For decades, physics has been built on these absolute giants, right? General relativity, the standard model, they're incredible. But what if the rulebook we're using to find the next big idea is, well, broken? Today, we're digging into a really bold proposal for a new way forward, a formal methodology called the New Territory Protocol. So here's how we're going to break it down. First, we'll look at the cracks that are starting to show in modern physics. Then, we'll get into the core philosophy behind this whole thing, a mandate of humility, before laying out the actual blueprint for new ideas. After that, we'll see how computer code can go head-to-head with the cosmos. And finally, we'll wrap up by thinking about what an engineer's approach to physics could really mean for the future.
All right, first things first. Why do we even need a new protocol in the first place? Well, the argument really kicks off with the idea that our most fundamental theories, as brilliant as they are, might just be hitting a wall.
And look, this isn't just some vague feeling people have. Even our absolute pillars of physics have well-known, well-defined limits. The standard model, for example, really struggles to explain things like mass and charge from scratch. And general relativity, it just kind of falls apart inside black holes. But here's the twist. For a field that's felt a bit stalled for a while, these aren't failures. The protocol argues they're actually opportunities, strategic openings for new ideas, but only if we come at them with a new kind of discipline.
This right here is the core critique. The protocol claims that way too much of modern physics lacks conceptual grounding. What does that mean? It means the core idea behind a theory is weak, even if the math is super complicated. And this leads to what it calls unconsumable theories. They're so abstract, so disconnected from reality, that they're basically useless for making predictions we can actually test.
I mean, we all love these huge, glamorous questions, right? What's inside a black hole? What's the deal with dark matter? But this new protocol says that chasing them directly right now is a total trap. They're unconsumable. We just don't have the tools to really digest them yet. Trying to answer them now just leads to wild speculation, not solid, testable science.
Okay, so if we can't tackle the biggest questions head-on, what's the alternative? Well, the answer starts with a pretty big philosophical shift. It's all about a mandate of humility.
This is the absolute cornerstone of the whole thing. The idea is to forget about finding the one final exact theory of everything. Instead, the focus completely shifts to building models that are functional and approximate. It's basically an admission that our tools, maybe even mathematics itself, have their limits. It's about being honest about what we just don't know.
And this way of thinking gives rise to a whole new kind of researcher, the physics engineer. Now, this is not your traditional theoretical physicist dreaming up equations at a blackboard. Nope. The physics engineer is a builder. Their goal is to create models that work, models that can be tested, and models that can be validated, even if they aren't some perfect final truth about the cosmos. So this isn't just some vague philosophical musings. It's a concrete, honest-to-goodness blueprint. It's a structured process designed to make sure that any new idea can actually stand on its own 2 feet.
And the progression here is strict. You can't skip steps. First, and this is the most important part, you need the concept. A clear, solid idea that you can explain. Only then do you bring in the math to describe it precisely. And finally, you design the experiments to test it. A theory without a solid concept is just a really detailed map of a place that doesn't exist.
This whole progression gets broken down even further into this 6-task framework. Think of it like a gauntlet, a serious stress test designed to turn a vague suggestion into a legitimate scientific work. It starts with a full concept, then uses math to formalize it. But here's a crucial step. It forces you to define your logic, what accurate enough even means, before you design the test, build the experiment, and finally, let the data be the judge. It's all about making sure the work itself is what matters, not just the reputation of the person who came up with it.
Okay, so this is where it gets really cool. You have a concept, you have the math, but how in the world do you test a new theory of physics if you can't just, build a particle accelerator in your garage? The answer? You build a universe inside a computer.
Validation here is all about comparison. It's that simple. You take the data we have from real-world experiments, and you put it side by side with the results that your computer simulation spits out. If your model can consistently create outputs that match what we actually see in reality, then your theory has earned its keep. The proof, as they say, is in the output.
And this is a perfect illustration of the protocol in action. This is a checklist for a real research program called New Perspective. And you can see exactly where it stands, clear as day. The conceptual work for quantum mechanics is listed as complete, but that critical next step, building the numerical tests, is still pending.
It's just a super transparent way to track progress and hold the research accountable.
So when you put all this together, what does it really add up to? It's a pretty fundamental shift in approach, isn't it? Moving from the really abstract heights of pure theory down to the grounded, hands-on work of engineering.
And if you boil it all down, this entire methodology really rests on 3 critical takeaways.
First, rigorous grounding. The idea, the concept is everything. It has to come first, no exceptions. Second, the humility of approximation. The goal here is to build functional models that actually work, not to chase after some perfect, unconsumable theory. And third, numerical validation. In a world where we can't always build physical experiments, a theory's ultimate test is its ability to replicate reality inside a computer.
Which leaves us with this final, pretty provocative thought. This protocol is suggesting a radical change in how we discover things about our universe. It's asking if the next great leap forward in physics won't come from a lone theorist with a blackboard, but from a pragmatic engineer with a supercomputer. So is the future of physics less about grand theory and more about practical, humble engineering?